In the vast expanse of the cosmos, there exists a phenomenon so powerful, so mysterious, that it defies the very laws of physics as we know them. Black holes, often called nature's ultimate enigmas, are more than just cosmic vacuum cleaners. They are the universe's most extreme laboratories, where gravity becomes so intense that not even light can escape. But what lies beyond the event horizon, that invisible boundary where the known rules of reality seem to break down? This is where the story gets even more fascinating. Scientists have spent decades unraveling the secrets of these celestial giants, and what they've discovered challenges everything we thought we knew about space, time, and the fabric of existence itself. In this video, we're diving deep into the heart of these cosmic mysteries. We'll explore how black holes form, what happens to matter once it crosses the point of no return, and the groundbreaking discoveries that are reshaping our understanding of the universe. From the mind-bending physics of singularity to the latest observations that are rewriting the textbooks, we'll uncover the science, the theories, and the unanswered questions that keep astronomers and physicists awake at night. So, buckle up, because by the end of this journey, you'll see black holes not just as cosmic oddities, but as keys to unlocking the deepest secrets of the cosmos. At the heart of every black hole lies a story of cosmic drama, a tale of stellar birth, life, and ultimately, a spectacular death. To understand how black holes come into existence, we need to rewind the clock and look at the life cycle of the most massive stars in the universe. These stars, often dozens of times more massive than our Sun, burn bright and fast, living lives that are both brilliant and brief. When such a star exhausts its nuclear fuel, the delicate balance between the outward pressure of radiation and the inward pull of gravity is shattered. Without the energy to counteract its own immense gravity, the star begins to collapse inward. This collapse is catastrophic, triggering a violent explosion known as a supernova, one of the most energetic events in the universe. The outer layers of the star are blasted into space, scattering elements like carbon, iron, and oxygen across the cosmos, which eventually become the building blocks of new stars, planets, and even life itself. But the story doesn't end there. What remains after the explosion is the star's core, now compressed under unimaginable pressure. If the core is massive enough, typically more than 3 times the mass of our Sun, gravity takes over completely, crushing it into an infinitely dense point called a singularity. This is the birth of a black hole, a region of space where gravity is so intense that nothing, not even light, can escape its pull. To visualize this process, think of a deflating balloon. As the air escapes, the balloon shrinks, its surface collapsing inward. In a similar way, the star's core collapses under its own gravity, but unlike a balloon, there's no limit to how far it can shrink. The matter is squeezed into a point so small and dense that it warps the very fabric of space and time around it. Black holes are more than just cosmic vacuum cleaners. They play a vital role in the universe's ecosystem. They act as both destroyers and creators, tearing apart stars and galaxies, while also seeding the cosmos with the raw materials needed for new structures to form. Without black holes, the universe as we know it might look very different. As we peel back the layers of these cosmic enigmas, the next question arises: what exactly happens at the edge of a black hole? What is this mysterious boundary we call the event horizon, and why is it so significant? The answers lie just beyond the threshold of our current understanding, in a place where the rules of physics as we know them begin to unravel. The anatomy of a black hole is as mesmerizing as it is intimidating. At its core lies the singularity, a point of infinite density where the laws of physics as we understand them cease to function. But before we reach this mysterious center, we encounter the event horizon, the black hole's defining feature. Imagine it as a one-way door. Once something crosses this boundary, there's no turning back. Not even light, the fastest thing in the universe, can escape its grasp. This invisible line marks the point where gravity's pull becomes unstoppable, creating a region of space that's forever hidden from our view. Surrounding the event horizon, we often find a dazzling spectacle, the accretion disk. Picture a swirling river of superheated gas and dust, spiraling inward at incredible speeds. As this material gets closer to the black hole, it heats up to millions of degrees, glowing brightly across the electromagnetic spectrum. This disk isn't just a visual marvel, it's also a source of immense energy, releasing radiation that can outshine entire galaxies. In some cases, the accretion disk fuels another extraordinary phenomenon, relativistic jets. These are narrow beams of charged particles that shoot out from the black hole's poles at nearly the speed of light, stretching across thousands of light years. These jets are so powerful that they can shape entire galaxies, influencing star formation and the evolution of cosmic structures. Each component of a black hole, the event horizon, the singularity, the accretion disk, and the jets, plays a crucial role in its behavior and impact on the surrounding universe. Together, they form a dynamic system that challenges our understanding of space and time. But what makes these cosmic giants tick? What forces and laws govern their existence? To answer these questions, we need to venture into the realm of black hole physics, where the bizarre becomes the norm and the impossible starts to feel inevitable. To truly grasp the physics of black holes, we need to step into the mind-bending world of Einstein's theory of general relativity. This groundbreaking theory redefined our understanding of gravity, not as a force in the traditional sense, but as the curvature of spacetime itself. Picture spacetime as a vast, invisible fabric, a rubber sheet stretched taut. When you place a heavy object, like a bowling ball, on this sheet, it creates a deep dent. In the same way, a black hole warps spacetime, creating a gravitational well so profound that nothing can climb out once it falls in. This is why black holes are often described as cosmic sinks. Once something crosses the event horizon, it's destined to spiral inward, pulled by the irresistible curve of spacetime. One of the most fascinating consequences of this warping is time dilation. Near a black hole, time doesn't flow the same way it does here on Earth. Imagine two astronauts, one stays far from the black hole, while the other ventures close to the event horizon. To the distant astronaut, time for their companion appears to slow down dramatically. Minutes for the brave explorer near the black hole could stretch into years or even centuries for the observer far away. This isn't just science fiction. It's a real prediction of Einstein's equations, confirmed by observations of objects orbiting near black holes, but the distortions don't stop there. As objects approach a black hole, they experience a phenomenon whimsically called spaghettification. The intense gravitational pull near the singularity isn't uniform, it's stronger on the side of the object closer to the black hole. This difference in force stretches the object, pulling it into long, thin strands like cosmic spaghetti. Imagine a star venturing too close to a black hole. Its outer layers would be ripped apart, stretched and compressed into a glowing stream of plasma before disappearing into the abyss. Yet, even black holes aren't entirely eternal. Thanks to the work of physicist Stephen Hawking, we've learned that black holes can slowly lose mass through a process known as Hawking radiation. This phenomenon occurs at the quantum level, where particles and antiparticles constantly pop in and out of existence near the event horizon. Occasionally, one of these particles escapes, carrying away a tiny bit of the black hole's energy. Over unimaginable timescales, this process can cause a black hole to evaporate entirely. It's a reminder that even the most dominant forces in the universe are subject to the strange rules of quantum mechanics. Black holes are laboratories of the extreme, where the familiar laws of physics are pushed to their limits. They challenge our understanding of reality, forcing us to rethink concepts like space, time, and matter. But as we peel back the layers of these cosmic mysteries, one question lingers: what happens beyond the event horizon? What secrets lie hidden in the heart of a black hole, where the rules of physics as we know them may no longer apply? The answers to these questions could reshape our understanding of the universe itself and hint at realities far stranger than we've ever imagined. Beyond the event horizon lies a realm where our understanding of the universe begins to unravel. This is the domain of the singularity, a point where matter is compressed to infinite density, and the laws of physics as we know them cease to function. It's a place where time and space lose their meaning, and the very fabric of reality bends beyond recognition. But what exactly happens here? The truth is, we don't fully know. The singularity is shrouded in mystery, hidden behind the event horizon's impenetrable veil. Yet, scientists have proposed some fascinating theories to help us glimpse the unimaginable. One of the most intriguing ideas is that black holes could be gateways to other parts of the universe, or even to entirely different universes. This concept ties into the theory of wormholes, hypothetical tunnels through spacetime that could connect distant regions or even different realities. Imagine folding a piece of paper so that 2 points touch. A wormhole would be like poking a hole through that fold, creating a shortcut. While wormholes remain purely theoretical, they offer a tantalizing possibility that black holes might not be the cosmic dead ends we once thought, but rather portals to places beyond our wildest imagination. But what would it be like to enter a black hole and approach the singularity? Through thought experiments, we can explore this scenario. Picture an astronaut crossing the event horizon. To an outside observer, the astronaut would appear to freeze in time, stretched and red-shifted by the intense gravitational pull. But from the astronaut's perspective, the journey would be far more bizarre. As they approach the singularity, tidal forces would stretch their body into a thin strand, a process known as spaghettification. Time would warp in strange ways, and the laws of physics as we know them would break down completely. It's a journey into the unknown, where the rules of reality no longer apply. Some theories even suggest that black holes might harbor alternate dimensions or universes within them. In this view, the singularity could be a bridge to a parallel reality, where the laws of physics are entirely different. While this idea sounds like science fiction, it stems from serious scientific inquiry, particularly in the field of quantum gravity. Researchers are still grappling with how to reconcile the behavior of black holes with the principles of quantum mechanics, and these speculative ideas are part of that ongoing exploration. Black holes challenge us to rethink our understanding of the universe, pushing the boundaries of what we consider possible. They are not just cosmic phenomena, they are windows into the deepest mysteries of existence. As we continue to probe their secrets, we may uncover clues about the nature of spacetime, the origins of the universe, and even the existence of realities beyond our own. But for now, the heart of a black hole remains one of the greatest enigmas in science, a place where the known gives way to the unknown, and the familiar dissolves into the extraordinary. And as we ponder the mysteries within black holes, we can't help but wonder about their role in the larger cosmic story. How do these enigmatic objects shape the universe around them? What influence do they have on the formation of galaxies, the birth of stars, and the evolution of the cosmos itself? These questions take us beyond the event horizon and into the broader tapestry of the universe, where black holes play a surprisingly active and dynamic role. Black holes are not just isolated cosmic oddities, they are integral players in the universe's grand design, weaving themselves into the very fabric of the cosmos. At the heart of nearly every galaxy, including our own Milky Way, lies a supermassive black hole, millions or even billions of times more massive than the Sun. These colossal entities act as gravitational anchors, shaping the galaxies around them and influencing their evolution over billions of years. But how do they achieve this? The answer lies in their immense gravitational pull, which not only governs the motion of stars and gas within their host galaxies, but also plays a crucial role in the formation of the cosmic web, the vast, interconnected network of galaxies that stretches across the universe. One of the most dramatic ways black holes impact their surroundings is through quasars. These are among the brightest objects in the universe, powered by supermassive black holes consuming enormous amounts of matter. As gas and dust spiral into the black hole, they form an accretion disk that heats up to extreme temperatures, releasing staggering amounts of energy. This energy can outshine entire galaxies, making quasars visible from billions of light years away. But quasars are more than just cosmic beacons, they also act as cosmic engines, driving the growth and evolution of galaxies. The intense radiation and powerful jets emitted by quasars can heat surrounding gas, preventing it from collapsing to form new stars. In this way, black holes help regulate the star formation process, ensuring that galaxies evolve in a balanced and controlled manner. Black holes also play a surprising role as cosmic recyclers. When material falls into a black hole, not all of it is lost forever. Some of it is ejected back into space in the form of energetic outflows and jets, redistributing matter and energy across vast distances. These outflows can travel far beyond their host galaxies, enriching intergalactic space with heavy elements like carbon, oxygen, and iron. Over time, this recycled material becomes the building blocks for new stars, planets, and even life itself. In this way, black holes contribute to the cycle of cosmic creation and destruction, ensuring that the universe remains a dynamic and ever-changing place. The interconnectedness of galaxies and black holes is a testament to the intricate balance of forces that govern the universe. Visualizing this relationship reveals a cosmic dance where black holes act as both creators and destroyers, shaping the large-scale structure of the cosmos. From the birth of galaxies to the distribution of matter across the universe, black holes are at the center of it all, orchestrating the evolution of the cosmic web. As we marvel at the profound influence of black holes, we're led to wonder, what groundbreaking discoveries lie ahead in our quest to understand these enigmatic objects? From cutting-edge telescopes to innovative theoretical models, scientists are uncovering new insights that are reshaping our understanding of black holes and their role in the universe. The next chapter in this cosmic journey promises to reveal even more about the secrets that lie beyond the event horizon. The journey to uncover the secrets of black holes has been nothing short of extraordinary, a story filled with bold predictions, groundbreaking discoveries, and moments that have reshaped our understanding of the universe. It all began not with telescopes or high-tech instruments, but with the power of human imagination and mathematics. In the late 18th century, British geologist and astronomer John Michell imagined a star so massive that its gravity could prevent light from escaping. Around the same time, French mathematician Pierre-Simon Laplace independently theorized about dark stars, celestial bodies so dense that they could trap light. These early ideas were the seeds of what we now know as black holes, though it would take more than a century for the concept to fully take root in the scientific community. Fast forward to the 20th century, and black holes moved from theoretical possibility to observable reality. In 1971, astronomers made a monumental discovery, Cygnus X1, the first black hole ever identified in our galaxy. This celestial object, located in the constellation Cygnus, revealed itself not through light, but through the X-rays it emitted as it devoured matter from a nearby star. This was the smoking gun, proof that black holes weren't just figments of mathematical imagination, but real, tangible phenomena lurking in the cosmos. But the story doesn't end there. In April 2019, humanity achieved what once seemed impossible, capturing an image of a black hole. Using the Event Horizon Telescope, a global network of radio telescopes, scientists unveiled the first ever picture of a supermassive black hole at the heart of the galaxy Messier 87. This historic image, showing a glowing ring of light surrounding a dark shadow, was a triumph of technology and collaboration. It not only confirmed the existence of black holes, but also provided a stunning visual of the event horizon, the point of no return for the first time in history. More recently, the study of black holes has entered a new era with the detection of gravitational waves, ripples in spacetime, caused by cataclysmic events such as black hole mergers. Since the first detection in 2015, these waves have opened a new window into the universe, allowing us to listen to the collisions of black holes billions of light years away. These observations have revealed the existence of intermediate mass black holes, bridging the gap between smaller stellar black holes and the supermassive giants at the centers of galaxies. Each discovery adds another piece to the puzzle, helping us understand the diverse roles black holes play in the cosmos. From Michell and Laplace's early musings to the latest gravitational wave detections, the study of black holes has been a journey of persistence and ingenuity. Yet for all we've learned, these cosmic enigmas continue to challenge us. The very nature of black holes hidden behind event horizons and governed by extreme physics makes them some of the most difficult objects to study. But as history has shown, where there's a mystery, there's also the potential for discovery. And as we continue to probe the depths of these cosmic giants, who knows what secrets we'll uncover next? Studying black holes is a bit like trying to solve a cosmic puzzle with half the pieces missing. These enigmatic objects are, by their very nature, invisible. Unlike stars or galaxies, black holes don't emit light or any form of radiation that we can directly observe. Instead, scientists must rely on indirect methods to study them, piecing together clues from their effects on the surrounding environment. It's detective work on a galactic scale, where every observation is a breadcrumb leading us closer to understanding these elusive phenomena. One of the primary challenges is the sheer distance and scale involved. Black holes are often millions or even billions of light years away, making them incredibly difficult to observe in detail. To study them, astronomers use a variety of techniques, such as tracking the movement of stars or gas clouds near a black hole. When these objects orbit or fall into a black hole, they emit radiation X-rays, gamma rays, or even radio waves that can be detected by telescopes. This is how we first discovered Cygnus X1, the black hole that confirmed their existence. But even with these methods, the data is often incomplete, leaving scientists to fill in the gaps with theoretical models and simulations. Another hurdle is the need for cutting-edge technology. Capturing the first image of a black hole in 2019 required an unprecedented global effort. The Event Horizon Telescope, a network of radio telescopes spanning the Earth, had to work in unison to collect enough data to create the now iconic image of the black hole in Messier 87. This feat was only possible because of advancements in computational power, which allowed scientists to process vast amounts of data and reconstruct the image. Even then, the result was a blurry ring of light surrounding a dark void, a testament to the immense challenges of observing something that, by definition, cannot be seen. Simulations play a crucial role in bridging the gap between observation and theory. By creating detailed computer models, scientists can predict how black holes behave under different conditions, from the formation of accretion disks to the emission of relativistic jets. These simulations are like virtual laboratories, allowing researchers to test hypotheses and explore scenarios that would be impossible to observe directly. For instance, simulations have helped us understand how black holes merge, producing gravitational waves that ripple through spacetime. Yet, even with these tools, the complexity of black hole physics means that many questions remain unanswered. The challenges of studying black holes are immense, but they also drive innovation and collaboration across the scientific community. Each discovery, whether it's a new gravitational wave signal or a sharper image of an event horizon, brings us one step closer to unraveling the mysteries of these cosmic giants. And as we push the boundaries of technology and theory, we're not just learning about black holes, we're expanding our understanding of the universe itself. But black holes aren't just the domain of scientists and researchers. They've also captured the imagination of storytellers, artists, and filmmakers, becoming iconic symbols in popular culture. From science fiction blockbusters to thought-provoking novels, black holes have inspired countless tales of exploration, danger, and wonder. So, as we step away from the challenges of science, let's explore how black holes have shaped our stories and what they reveal about our fascination with the unknown. Black holes have long fascinated not just scientists, but also creators of art, literature, and film. These cosmic enigmas, with their mysterious and awe-inspiring nature, have become powerful symbols in popular culture, representing everything from the unknown to the transformative. Take, for example, Christopher Nolan's epic film Interstellar. The movie's portrayal of a supermassive black hole, Gargantua, was grounded in real science, thanks to the guidance of physicist Kip Thorne. The film's stunning visual effects brought to life the warping of space-time and the mind-bending concept of time dilation, giving audiences a glimpse of what it might be like to venture near the edge of a black hole. Yet it also took creative liberties, using the black hole as a narrative device to explore themes of love, sacrifice, and the human spirit's resilience. On the other hand, films like Event Horizon take a darker, more speculative approach. Here, black holes serve as gateways to chaos and horror, embodying humanity's fear of the unknown. While the science in this film is far from accurate, its portrayal taps into a deeper psychological truth. Black holes, as cosmic voids, evoke a primal sense of dread and wonder. They become metaphors for the limits of human understanding, pushing us to confront questions about existence, morality, and what lies beyond the boundaries of our reality. In literature, black holes often symbolize transformation and the unknown. Authors like Arthur C. Clarke and Carl Sagan have used them as backdrops for stories about exploration and discovery. In Clarke's 2001, A Space Odyssey, the monolith, a mysterious alien artifact, could be seen as a metaphorical black hole challenging humanity to evolve and transcend its limitations. Similarly, Sagan's Contact explores the idea of communication across vast cosmic distances, with black holes serving as gateways to new realms of possibility. These stories remind us that black holes aren't just physical phenomena, they're also mirrors reflecting our deepest hopes and fears. Artists, too, have been captivated by black holes, using them as inspiration for works that blur the line between science and imagination. From surreal paintings to experimental digital art, black holes are often depicted as swirling vortices of light and shadow, evoking a sense of infinite depth and mystery. These artistic interpretations remind us that black holes are more than just objects of study, they are sources of inspiration, inviting us to ponder the mysteries of the universe in new and creative ways. Scientific discoveries have also shaped how black holes are portrayed in culture. The first image of a black hole, captured in 2019, not only made headlines but also influenced how filmmakers and artists conceptualize these objects. The now iconic image of the glowing ring of light surrounding a dark void has become a cultural touchstone, appearing in everything from documentaries to album covers. This interplay between science and art highlights how our understanding of black holes evolves, shaping how we depict them in stories and visuals. Black holes, in all their complexity, have become more than just cosmic phenomena. They are cultural icons, symbols of the human quest to understand the unknown. They challenge us to think beyond the limits of our knowledge, inspiring both awe and curiosity. And as we continue to explore their mysteries, we're reminded that the line between science and storytelling is often thinner than we think. But the fascination with black holes doesn't stop at art and entertainment. These enigmatic objects also raise profound philosophical questions about the nature of existence, the limits of human understanding, and the very fabric of reality. What do black holes tell us about the universe and about ourselves? These are the questions we'll explore next, as we delve into the philosophical implications of these cosmic giants. Black holes are not just scientific curiosities, they are profound philosophical puzzles that force us to confront the very nature of reality. What does it mean for something to exist in a place where time and space lose their meaning? How do we define causality when the rules of cause and effect break down at the edge of a singularity? These are the kinds of questions that arise when we consider the deeper implications of black holes, and they challenge us to rethink some of our most fundamental assumptions about the universe. One of the most striking philosophical dilemmas posed by black holes is their relationship with time. In our everyday lives, time flows in one direction, from past to future. But near a black hole, this familiar progression is disrupted. Time slows down dramatically as you approach the event horizon, and at the singularity, it may cease to exist altogether. This raises profound questions. If time can stretch and warp, is it truly a fixed and universal concept? Or is it something more fluid, shaped by the forces of gravity and the structure of spacetime? These questions don't just apply to black holes, they ripple outward, challenging our understanding of time itself. Another philosophical frontier is the concept of information. According to quantum mechanics, information about the state of a system can never be truly lost, But black holes seem to defy this principle. When matter falls into a black hole, it's compressed into a singularity, leaving no trace of its original form. This apparent contradiction, known as the information paradox, has sparked heated debates among physicists and philosophers alike. Some suggest that the information might be encoded on the event horizon, a concept known as the holographic principle. Others propose that it's radiated away through Hawking radiation. These ideas push us to reconsider what we mean by information and whether it's truly fundamental to the fabric of reality. Black holes also invite us to explore the boundaries of human knowledge. They are cosmic laboratories where the laws of physics are pushed to their limits, revealing gaps in our understanding. For instance, the singularity at the heart of a black hole is a place where our current theories, general relativity, and quantum mechanics break down. This suggests that there's a deeper, more unified theory waiting to be discovered, one that can reconcile the behavior of the very large with the very small. In this sense, black holes are not just mysteries to be solved, they are guides, pointing us toward a more complete understanding of the universe. The philosophical implications of black holes extend even further when we consider the possibility that they might contain entire universes or serve as gateways to other realities. Could a black hole be a portal to a parallel universe, where the laws of physics are entirely different? This idea, while speculative, challenges us to think beyond the observable universe and consider the existence of realities that lie beyond our grasp. It's a reminder that the cosmos is far stranger and more complex than we can imagine, and that black holes might hold the keys to unlocking its deepest secrets. As we reflect on these profound questions, it's clear that black holes are more than just cosmic phenomena. They are mirrors, reflecting our own curiosity and desire to understand the universe. They remind us that science is not just about answers, but about asking the right questions. And as we continue to explore these enigmatic objects, we're not just learning about black holes, we're learning about the nature of existence itself. But the journey doesn't end here. As we push the boundaries of our knowledge, new questions emerge, and new technologies promise to reveal even more about these cosmic enigmas. What lies ahead in the future of black hole research? The next chapter in this story is already being written, and it promises to be as thrilling as the discoveries that have come before. The future of black hole research is brimming with possibilities, fueled by cutting-edge technologies and ambitious missions that promise to revolutionize our understanding of these cosmic enigmas. Imagine a world where we can peer deeper into the universe than ever before, uncovering secrets that have remained hidden for billions of years. This isn't science fiction, it's the reality of what lies ahead in the next chapter of black hole exploration. One of the most exciting tools on the horizon is the James Webb Space Telescope, or JWST. Launched in late 2021, this marvel of engineering has already begun to transform our view of the cosmos. With its unparalleled sensitivity to infrared light, JWST can observe the faintest glimmers of ancient galaxies, some of which host supermassive black holes at their cores. By studying these distant objects, scientists hope to unravel how black holes formed in the early universe and how they influenced the birth and evolution of galaxies. It's like having a time machine that takes us back to the dawn of cosmic history, offering clues about the origins of everything we see today. But JWST is just the beginning. Looking further ahead, the Laser Interferometer Space Antenna, or LISA, is set to take black hole research to new heights literally. Unlike ground-based observatories, LISA will be a space-based gravitational wave detector, designed to sense ripples in spacetime caused by massive events like black hole mergers. Scheduled for launch in the 2030s, LISA will allow us to listen to the universe in ways we never could before, capturing the faint echoes of collisions that occurred billions of years ago. This mission could reveal entirely new classes of black holes, including intermediate mass black holes, which have so far eluded detection. It's a game changer, opening a new window into the hidden symphony of the cosmos. Beyond these missions, artificial intelligence is playing an increasingly vital role in black hole research. With the sheer volume of data generated by modern telescopes, analyzing it all manually would be impossible. That's where AI steps in, sifting through mountains of information to identify patterns, anomalies, and potential discoveries. Machine learning algorithms have already been used to refine images of black holes and predict the behavior of accretion disks. As AI technology advances, it could help us uncover entirely new phenomena, from the nature of dark matter to the elusive connections between black holes and the origins of the universe. The potential for discovery is staggering. Could black holes hold the key to understanding dark matter, the mysterious substance that makes up most of the universe's mass? Some theories suggest that dark matter particles might interact with black holes in ways we've yet to detect. Others propose that black holes themselves could be made of dark matter, or that they might even act as portals to other dimensions. These ideas, while speculative, push the boundaries of our imagination and challenge us to think beyond the limits of current science. As we stand on the brink of these breakthroughs, it's impossible not to feel a sense of awe and anticipation. The tools and technologies at our disposal are more powerful than ever, and the mysteries they aim to solve are as profound as they are perplexing. But the story of black holes doesn't end with their physics or their role in the universe. It extends to the very fabric of life itself. Could black holes play a part in the search for extraterrestrial life? The answer might be closer than we think. When we think about the search for extraterrestrial life, black holes might not be the first place we'd look. After all, these cosmic behemoths are known for their destructive power, ripping apart stars and consuming anything that ventures too close. But what if the story isn't so straightforward? What if, hidden in the chaos of these extreme environments, life, or something resembling it, could exist in ways we've never imagined? This is where the boundaries of science and speculation blur, opening up a realm of possibilities that challenge our understanding of what life could be. Let's start with the basics. The environment near a black hole is anything but hospitable. The intense gravitational forces, extreme radiation, and chaotic tidal effects make it seem like a place where life as we know it couldn't survive. But life on Earth has taught us that organisms can thrive in the most unexpected places: deep-sea vents, acidic hot springs, and even the vacuum of space. Could life adapt to the harsh conditions near a black hole? Some scientists speculate that microbial life, or even more complex organisms, might exist in the accretion disks surrounding black holes. These swirling disks of gas and dust are incredibly energetic, but they also contain regions where temperatures and pressures might stabilize, creating pockets of habitability. It's a long shot, but in the vastness of the universe, stranger things have happened. Then there's the idea of advanced civilizations harnessing black holes for their own purposes. Imagine a society so technologically advanced that they've learned to tap into the immense energy of a black hole. The accretion disk, with its glowing plasma and powerful magnetic fields, could serve as a cosmic power plant, providing energy on a scale we can barely comprehend. Some theories even suggest that advanced beings might use black holes as gateways for travel, bending spacetime to traverse vast distances in the blink of an eye. While this sounds like science fiction, it's rooted in real physics, specifically the concept of wormholes, which some black holes might theoretically contain. If such civilizations exist, black holes could be the ultimate tool in their cosmic toolkit. But what about life existing within a black hole? This is where things get truly speculative. Some physicists have proposed that the singularity at the heart of a black hole might not be a dead end, but rather a gateway to another universe or dimension. In this scenario, life could exist in these alternate realities, completely unlike anything we've encountered. These exotic life forms might not rely on the same physical laws we do, thriving in conditions that would be impossible for us to comprehend. It's a radical idea, but it underscores just how little we truly understand about the nature of black holes and the potential for life in the universe. Of course, all of this is speculation, but that's part of what makes black holes so fascinating. They force us to think beyond the limits of our current knowledge, to imagine possibilities that stretch the boundaries of science and imagination. They remind us that the universe is full of mysteries waiting to be uncovered, and that life, in all its forms, might be far more resilient and adaptable than we ever thought. As we ponder these extraordinary ideas, another question arises. Could black holes hold the key to understanding one of the universe's greatest mysteries, dark energy? This enigmatic force, driving the accelerated expansion of the cosmos, has puzzled scientists for decades, and as we'll explore next, the connection between black holes and dark energy might be closer than we think, offering a tantalizing glimpse into the deepest secrets of the universe. Black holes and dark energy, two of the most enigmatic forces in the universe, might seem like entirely separate phenomena. One devours everything in its path, while the other pushes the cosmos apart at an accelerating rate. But what if these two cosmic heavyweights are more connected than we think? Delving into this relationship opens up a fascinating chapter in our understanding of the universe, one that could reshape our view of its past, present, and ultimate fate. At the heart of this mystery is dark energy, the elusive force driving the accelerated expansion of the universe. Discovered in the late 1990s, dark energy remains one of the greatest puzzles in modern cosmology. It's thought to make up about 68% of the universe's energy content, yet we still don't know what it truly is. Some theories suggest that dark energy permeates the fabric of spacetime itself, acting as a kind of cosmic pressure that counteracts gravity. But here's where black holes come into play. Could these gravitational behemoths, with their immense influence on spacetime, also interact with dark energy in surprising ways? One intriguing idea is that black holes might act as sources or sinks of dark energy. Imagine a black hole as a cosmic sponge, absorbing or releasing dark energy as it evolves. Some researchers propose that black holes could grow not just by swallowing matter, but also by drawing in dark energy from their surroundings. This would mean that black holes aren't just passive players in the universe, they could actively shape the distribution and behavior of dark energy on a cosmic scale. If true, this could help explain why the universe's expansion is accelerating and why it seems to be doing so faster over time, but the implications go even further. The interplay between black holes and dark energy could hold clues to the ultimate fate of the universe. One possibility is the Big Rip, a scenario where dark energy's influence becomes so overwhelming that it tears apart galaxies, stars, planets, and even atoms themselves. In this dramatic endgame, black holes might be the last structures standing, their immense gravity resisting the relentless pull of dark energy, at least for a while. Another possibility is the heat death, where the universe expands so much that it becomes cold, dark, and empty, with black holes slowly evaporating over trillions of years through Hawking radiation. Both scenarios paint a stark picture of the cosmos, and black holes could play a pivotal role in determining which path the universe ultimately takes. Visualizing this interplay is no small feat, but imagine the universe as a vast, expanding fabric. Dark energy stretches this fabric outward, while black holes act like weights, creating deep dimples that tug at the surrounding material. Over time, these dimples could influence how the fabric stretches, altering the rate and direction of cosmic expansion. It's a delicate dance between two opposing forces, one that could shape the destiny of everything we know. As we explore this cosmic tug-of-war, we're reminded just how interconnected the universe truly is. Black holes, once thought of as isolated oddities, are now being seen as key players in the grand cosmic drama. Their relationship with dark energy not only deepens our understanding of these mysterious forces, but also raises profound questions about the nature of existence itself. And as we continue to unravel these mysteries, we're led to yet another tantalizing possibility. Could black holes hold the key to time travel? This is the question we'll explore next, as we venture into the realm of theoretical physics and the mind-bending possibilities it presents. The idea of time travel has captivated humanity for centuries, fueling countless stories, dreams, and scientific inquiries. But what if the key to unlocking this elusive possibility lies in the most extreme environments in the universe, black holes? These cosmic giants, with their immense gravitational pull, warp spacetime in ways that challenge our understanding of reality. And within that warping, some scientists believe could lie the potential for time travel. It's a concept that sounds like pure science fiction, but it's rooted in the very real physics of Einstein's theory of general relativity. At the heart of this idea is the notion of closed time-like curves, or CTC. These are hypothetical paths through spacetime that loop back on themselves, allowing an object or even a person to return to the same point in time. In simpler terms, they're time loops. Near a black hole, the extreme curvature of spacetime could, in theory, create such loops. Picture a rubber sheet stretched tight, with a heavy object creating a deep dent. If you could move along the edges of that dent just right, you might find yourself traveling backward in time. While CTCs haven't been observed, they're mathematically possible under the equations of general relativity, making them a tantalizing area of study for physicists. But how could this work in practice? One possibility involves wormholes, hypothetical tunnels through spacetime that connect distant points or even different times. Imagine folding a piece of paper so that 2 points touch, then poking a hole through the fold. That's essentially what a wormhole would do, creating a shortcut through the fabric of the universe. Some theories suggest that black holes could serve as entrances to these tunnels, with the other end a white hole, spewing out matter in another place or time. If such wormholes exist, they could act as natural time machines, allowing for travel not just through space, but through time itself. Science fiction has long explored these ideas, often with thrilling and imaginative results. In Doctor Who, the TARDIS famously uses a wormhole-like mechanism to traverse time and space, while Star Trek has depicted black holes as gateways to alternate realities. These stories, while fictional, draw on real scientific concepts, sparking our curiosity about what might be possible. They remind us that the line between science and speculation is often thinner than we think, and that the universe may hold surprises far beyond our current understanding. Of course, the idea of time travel raises as many questions as it answers. What would happen if someone traveled back in time and changed the past? Could paradoxes, like the infamous grandfather paradox, be resolved, or would they unravel the fabric of reality? These questions aren't just philosophical, they're deeply tied to our understanding of causality and the nature of time itself. And while we may not have answers yet, exploring these possibilities pushes the boundaries of what we think is possible. Black holes, with their ability to bend and twist space-time, offer a unique window into these mysteries. They challenge us to rethink our assumptions and imagine a universe where time isn't linear, where the past, present, and future might be more interconnected than we ever thought. But as we ponder these extraordinary ideas, another question arises: what are the ethical implications of black hole research? If we ever unlock the secrets of time travel or harness the power of black holes, how should we use that knowledge? These are the questions we'll explore next, as we delve into the moral and philosophical dilemmas that come with probing the universe's deepest mysteries. As we continue our journey into the mysteries of black holes, we arrive at a question that often goes unasked, but is no less important. What are the ethical implications of studying these cosmic giants? While black holes may seem like distant, abstract phenomena, the knowledge we gain from them has the potential to reshape not just our understanding of the universe, but also our place within it. And with that knowledge comes responsibility, a responsibility to consider how this information is used, shared, and applied in ways that benefit humanity rather than harm it. One of the most pressing ethical questions revolves around the potential misuse of black hole-related technology. Imagine, for a moment, that we discover a way to create artificial black holes, tiny, controlled versions of these cosmic phenomena. On one hand, this could revolutionize energy production, propulsion systems, or even our understanding of spacetime itself. But on the other hand, what if such technology fell into the wrong hands? The immense power of black holes, even on a small scale, could be weaponized, leading to catastrophic consequences. It's a sobering thought, one that forces us to confront the dual-edged nature of scientific progress. This isn't just speculative. History is filled with examples of groundbreaking discoveries being used for both good and ill. The development of nuclear energy, for instance, brought us clean power, but also the atomic bomb. As we push the boundaries of black hole research, we must ask ourselves, how can we ensure that the knowledge we gain is used ethically? This question isn't just for scientists, it's for all of us. After all, the choices we make today will shape the future of humanity, and perhaps even the universe itself. Another ethical consideration is the way scientific discoveries are communicated to the public. Black holes are inherently mysterious and complex, which makes them ripe for misunderstanding or sensationalism. Misinformation can spread quickly, leading to fear, confusion, or even misguided policies. Scientists have a responsibility to share their findings in ways that are accurate, accessible, and grounded in reality. But this isn't always easy. How do you explain the intricacies of space-time curvature or quantum mechanics to someone without a background in physics? Striking that balance between clarity and accuracy is no small task, but it's essential for fostering a well-informed society. At the same time, the public also has a role to play. In an age of information overload, it's more important than ever to approach sensational headlines with a critical eye. Are we being told the full story, or is the truth being distorted for clicks and views? By engaging thoughtfully with scientific discoveries, we can help ensure that the conversation around black holes and science in general remains grounded and productive. These ethical dilemmas extend even further when we consider the broader implications of black hole research. What if we discover that black holes are gateways to other universes, or that they hold the key to manipulating spacetime itself? Such discoveries could fundamentally alter our understanding of reality, raising profound questions about identity, existence, and our place in the cosmos. Are we prepared to grapple with these questions? And if not, how do we get there? As we reflect on these challenges, one thing becomes clear: the study of black holes isn't just about unraveling cosmic mysteries. It's also about understanding ourselves, our values, our responsibilities, and our potential as a species. And as we venture deeper into the unknown, we're reminded that every discovery comes with a choice: to use our knowledge wisely or to let it lead us astray. But the ethical considerations of black hole research are just one piece of the puzzle. What if black holes are more than just isolated phenomena? What if they are part of a much larger cosmic tapestry, one that includes not just our universe, but countless others? This is the intriguing possibility we'll explore next, as we dive into the role of black holes in the multiverse theory. What if our universe isn't the only one? What if, beyond the edge of a black hole, lies a doorway to another reality entirely? This is the tantalizing idea behind the multiverse theory, a concept that suggests our universe might be just one of countless others, each with its own unique laws of physics and possibilities. And at the heart of this theory, black holes might hold the key. These cosmic enigmas, with their ability to warp spacetime to unimaginable extremes, could be more than just celestial phenomena. They might be bridges to other dimensions, gateways to realities beyond our wildest imagination. The idea that black holes could connect our universe to others stems from the concept of wormholes, hypothetical tunnels through spacetime that link distant points or even separate universes. Picture a piece of paper folded in half with 2 points touching. If you poke a hole through the fold, you create a shortcut between those points. In the same way, a wormhole could theoretically connect 2 regions of space, or even 2 entirely different universes. Some scientists propose that black holes, with their intense gravitational fields, could serve as the entrances to these cosmic tunnels. If true, this would mean that black holes aren't just endpoints for matter, but portals to entirely new realms. But what would these other universes look like? The possibilities are as vast as the multiverse itself. In some scenarios, these parallel realities might be nearly identical to our own, with only subtle differences, like a world where dinosaurs never went extinct, or where humans evolved in entirely new ways. In others, the laws of physics could be completely alien, with different constants, forces, and even dimensions. Imagine a universe where gravity is 10 times stronger, or where time flows backward. These speculative scenarios stretch the limits of our imagination, challenging us to think beyond the familiar confines of our own reality. The implications of such a discovery would be profound. If black holes truly are gateways to other universes, it would revolutionize our understanding of existence itself. No longer would our universe be seen as an isolated bubble in the void. It would be part of an interconnected web of realities, each with its own unique story. This idea also raises philosophical questions. If other universes exist, do they have their own versions of us? Could we ever communicate with these parallel realities, or even travel to them? These are questions that blur the line between science and science fiction, but they are rooted in real theoretical physics. One of the most intriguing aspects of this theory is its connection to the concept of the multiverse. In some versions of the multiverse hypothesis, every possible outcome of every event exists in its own separate universe. This means that somewhere out there, in the vast expanse of the multiverse, every decision you've ever made, and every decision you didn't make, is playing out in a parallel reality. Black holes, as potential gateways, could be the threads that weave this cosmic tapestry together, linking these infinite possibilities into a single, interconnected whole. Of course, this is all speculative for now. The multiverse theory remains one of the most controversial and debated ideas in modern physics, but even if we never find definitive proof, the concept itself is a testament to the power of human curiosity. It pushes us to explore the boundaries of our knowledge, to ask questions that challenge our understanding of reality, and to dream of possibilities that lie beyond the horizon of what we can currently see. As we ponder these extraordinary ideas, another question arises: how did black holes shape the early universe? If they're capable of connecting realities, could they also have played a role in the birth of our own cosmos? This is the mystery we'll explore next, as we journey back in time to uncover the origins of black holes and their influence on the universe's first moments. To understand the origins of the universe, we need to rewind the cosmic clock back to its earliest moments, a time when the universe was a seething cauldron of energy, just seconds old. In these extreme conditions, the seeds of black holes may have already been sown. These aren't the black holes we're familiar with, born from the collapse of massive stars. These are primordial black holes, hypothetical objects thought to have formed in the chaotic aftermath of the Big Bang. Unlike their stellar counterparts, primordial black holes could have emerged from the tiniest fluctuations in density regions where matter was packed so tightly that gravity took over, collapsing them into black holes no larger than an atom or as massive as a star. The idea of primordial black holes is fascinating because it suggests that black holes weren't just products of the universe's evolution, they were part of its very foundation. If these objects existed, they could have played a crucial role in shaping the cosmos as we know it. For instance, their immense gravitational pull might have acted as cosmic anchors, drawing in gas and dust to form the first stars and galaxies. In this way, primordial black holes could have been the architects of the universe, laying the groundwork for the structures we see today, but their influence might not stop there. Some scientists speculate that these ancient black holes could even explain one of the universe's greatest mysteries, dark matter. While we can't see dark matter directly, we know it exists because of its gravitational effects on galaxies and galaxy clusters. Primordial black holes, if they're abundant enough, could account for at least a portion of this elusive substance. Imagine a universe filled with countless tiny black holes, invisible yet omnipresent, weaving the cosmic web of dark matter that holds galaxies together. It's a compelling idea, though one that remains unproven for now. To visualize this early universe, picture a vast, expanding sea of energy and matter, punctuated by these gravitational hotspots. As the universe cooled and expanded, these black holes would have grown, merging with one another and influencing the distribution of matter around them. Over billions of years, their combined effects could have shaped the large-scale structure of the cosmos, from the filaments of the cosmic web to the clusters of galaxies we observe today. It's a cosmic dance where black holes lead the way, guiding the universe's evolution from chaos to order. Yet, despite their potential significance, primordial black holes remain elusive. We've yet to detect them directly, and their existence is still a matter of debate, but the search is far from over. Scientists are using a variety of methods, from gravitational wave detectors to telescopes scanning the skies for telltale signs, to hunt for these ancient relics. Each discovery, or even the absence of one, brings us closer to understanding the universe's origins and the role black holes played in its infancy. As we explore these cosmic beginnings, we're reminded that black holes are more than just destructive forces, they're also creators, shaping the universe in ways we're only beginning to comprehend. But their story doesn't end in the distant past. It extends into the realm of the infinitesimally small, where the bizarre rules of quantum mechanics come into play. What happens when we combine the immense gravity of black holes with the strange, counterintuitive world of quantum physics? This is the frontier we'll explore next, as we dive into the fascinating intersection of black holes and quantum mechanics. When we think about black holes, we often picture them as gravitational behemoths, devouring everything in their path. But what happens when we zoom way in, to the tiniest scales of the universe? This is where the bizarre and fascinating world of quantum mechanics comes into play, and where black holes reveal yet another layer of their mystery. Quantum mechanics, the science of the very small, governs the behavior of particles at the atomic and subatomic level. It's a realm where the usual rules of physics break down, replaced by probabilities, uncertainties, and phenomena that seem almost magical. But when quantum mechanics meets the immense gravity of black holes, the result is a cosmic puzzle that has left scientists scratching their heads for decades. At the heart of this puzzle is the information paradox. In the quantum world, information is sacred. The laws of quantum mechanics tell us that information about the state of a system, whether it's a single particle or an entire star, can never be truly lost. But black holes seem to defy this principle. When matter falls into a black hole, it's crushed into a singularity, leaving no trace of its original form. So, where does the information go? Does it vanish forever, or is it somehow preserved? This question has sparked one of the most heated debates in modern physics, with implications that reach far beyond black holes themselves. One of the most intriguing solutions to this paradox is the holographic principle. This theory suggests that all the information about what falls into a black hole isn't lost. It's encoded on the black hole's surface, specifically on its event horizon. Think of it like a cosmic DVD. When you watch a movie, the three-dimensional scenes you see are actually stored on a flat, two-dimensional disk. In the same way, the holographic principle proposes that the three-dimensional information inside a black hole is projected onto its two-dimensional surface. It's a mind-bending idea, but it offers a way to reconcile the apparent loss of information with the rules of quantum mechanics. To make this even more relatable, imagine a library filled with books. If the library burns down, the information in those books seems lost forever. But what if, before the fire, every page of every book had been meticulously copied onto the walls of the library? The information would still exist, just in a different form. In the case of a black hole, the event horizon acts like those walls, preserving the information of everything that falls in, even if we can't see it directly. But the holographic principle isn't the only theory attempting to solve the information paradox. Another idea involves Hawking radiation, the faint glow of particles that black holes emit over time. Some scientists believe that this radiation could carry away the information about the matter that fell into the black hole, encoding it in subtle ways. It's like a cosmic whisper, preserving the secrets of the universe even as the black hole itself fades away. These theories don't just solve a puzzle, they challenge our understanding of reality itself. They suggest that the universe might be far more interconnected and holographic than we ever imagined, with information playing a central role in the fabric of existence. And as we grapple with these ideas, we're reminded that black holes aren't just cosmic oddities, they're windows into the deepest mysteries of the universe. But the story doesn't end here. The intersection of black holes and quantum mechanics is about more than just solving paradoxes. It's about uncovering the fundamental laws that govern everything. Could black holes hold the key to a theory of everything, a single framework that unites quantum mechanics with gravity and explains the universe as a whole? This is the tantalizing question we'll explore next, as we delve into the quest for the ultimate theory of reality. At the heart of modern physics lies a monumental challenge, unifying the two pillars of our understanding of the universe: general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes the universe on the grandest scales, governing the motion of planets, stars, and galaxies through the curvature of spacetime. Quantum mechanics, on the other hand, rules the realm of the very small, dictating the behavior of particles at the atomic and subatomic level with an uncanny precision. But when these two frameworks collide, particularly in the extreme environment of a black hole, the result is a cosmic clash that leaves scientists scratching their heads. Black holes, with their immense gravitational pull and mind-bending distortions of spacetime, are the ultimate testing ground for this unification. Near the event horizon, where gravity is at its strongest, the predictions of general relativity and quantum mechanics diverge dramatically. According to relativity, matter falling into a black hole is crushed into a singularity, a point of infinite density where the laws of physics break down. But quantum mechanics tells us that information can never be truly lost, creating a paradox that has puzzled physicists for decades. How can these two seemingly incompatible theories be reconciled? The answer might lie in a theory of everything, a single framework that bridges the gap between the very large and the very small. One of the most promising candidates for such a theory is string theory. At its core, string theory suggests that the fundamental building blocks of the universe aren't particles, as we've long thought, but tiny, vibrating strings of energy. These strings, depending on how they vibrate, give rise to all the particles and forces we observe. What's more, string theory naturally incorporates gravity, offering a potential path to unifying it with quantum mechanics. In the context of black holes, string theory provides a way to resolve the information paradox, suggesting that the information swallowed by a black hole isn't lost but encoded in the vibrations of these strings. It's a beautiful idea, but one that remains unproven, at least for now. Another approach comes from loop quantum gravity, which attempts to quantize spacetime itself. Instead of treating spacetime as a smooth, continuous fabric, loop quantum gravity proposes that it's made up of tiny, discrete loops, like a cosmic tapestry woven from threads. This theory offers a way to avoid the singularities predicted by general relativity, suggesting that black holes might not be the infinite pits we once thought, but rather gateways to new regions of spacetime. While still in its early stages, loop quantum gravity provides a fresh perspective on the nature of black holes and the universe as a whole. The quest for a unified theory isn't just an academic exercise, it's a journey to uncover the fundamental laws that govern everything. Imagine the universe as a vast puzzle, with each discovery bringing us closer to seeing the full picture. Black holes, with their extreme conditions and paradoxical behavior, are like the missing pieces that could unlock the entire image. By studying them, we're not just learning about black holes, we're exploring the very fabric of reality itself. As we continue to probe these cosmic enigmas, one thing becomes clear: black holes are more than just objects of scientific curiosity. They are windows into the deepest mysteries of the universe, challenging us to rethink our understanding of space, time, and existence. And in this quest, they might just hold the key to a theory of everything, a single framework that unites the very large and the very small into a coherent whole. But the story doesn't end with theoretical physics. Black holes also play a crucial role in one of the most exciting areas of modern astronomy, the study of gravitational waves. These ripples in spacetime, first detected in 2015, have opened a new window into the cosmos, allowing us to listen to the collisions of black holes billions of light years away. What secrets do these waves hold, and how do they deepen our understanding of black holes and the universe as a whole? This is the frontier we'll explore next, as we dive into the revolutionary world of gravitational wave astronomy. The universe is filled with whispers, ripples in the fabric of spacetime that carry secrets from the most violent and energetic events in the cosmos. These whispers are gravitational waves, and their discovery has revolutionized how we study black holes. In 2015, scientists made history when they detected gravitational waves for the first time, confirming a prediction made by Albert Einstein a century earlier. This monumental achievement not only opened a new window into the universe, but also gave us a front-row seat to the dramatic collisions of black holes, events so powerful they literally bend the fabric of reality. Gravitational waves are born from cataclysmic events, such as the merging of two black holes. When these massive objects spiral toward each other, their immense gravity warps spacetime like ripples spreading across a pond. As they collide, they unleash a burst of energy so intense that it sends shockwaves through the cosmos, traveling at the speed of light. These ripples carry information about the black holes, their masses, spins, and even the shape of the spacetime around them. But detecting these waves is no small feat. They're incredibly faint by the time they reach Earth, requiring some of the most sensitive instruments ever built to capture their subtle signals. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two massive detectors, one in Louisiana and the other in Washington, each with arms stretching 2.5 miles long. Inside these detectors, lasers bounce back and forth between mirrors, measuring the tiniest distortions in spacetime caused by passing gravitational waves. When a wave passes through, it stretches and compresses space itself, altering the distance the laser light travels. This change is almost imperceptibly small, less than 1,000th the width of a proton, but LIGO precision is so extraordinary that it can detect this minuscule shift. It's like measuring the distance to the nearest star with the accuracy of a human hair. The first gravitational wave detected by LIGO came from the collision of two black holes, each about 30 times the mass of our Sun. As they spiraled closer, their immense gravity accelerated them to nearly half the speed of light. When they finally merged, they released more energy in a fraction of a second than all the stars in the observable universe combined. This energy rippled outward as gravitational waves, carrying the sound of the collision across billions of light years. The signal LIGO picked up was a brief chirp, a rising tone that marked the final moments before the black holes became one. Since that first detection, LIGO and its European counterpart, Virgo, have observed dozens of black hole mergers, each offering new insights into these cosmic giants. These observations have revealed black holes of all sizes, from a few times the mass of our Sun to behemoths weighing more than 100 solar masses. They've also provided clues about how black holes form and evolve, shedding light on their role in the universe's grand tapestry. For example, some of these mergers involve black holes spinning in opposite directions, suggesting they may have formed in chaotic environments like dense star clusters. Others hint at the existence of intermediate mass black holes, a long-sought class of objects that could bridge the gap between stellar black holes and supermassive ones. But the implications of gravitational wave astronomy go far beyond black holes. These ripples in spacetime are also a powerful tool for testing our understanding of gravity itself. Einstein's theory of general relativity has passed every test thrown at it so far, but black hole mergers push it to its limits. By comparing the gravitational waves we detect with the predictions of relativity, scientists can look for any deviations that might hint at new physics. It's like using black holes as cosmic laboratories, probing the very nature of spacetime and the forces that shape it. As we listen to the universe's whispers, we're uncovering a symphony of black hole collisions, neutron-star mergers, and other cosmic events that were once hidden from us. Gravitational waves have transformed our understanding of the universe, revealing its dynamic and interconnected nature in ways we never imagined. And as we continue to refine our instruments and expand our observations, who knows what other secrets these ripples in spacetime will reveal. But the story of black holes doesn't end with gravitational waves. These cosmic enigmas also play a surprising role in another of the universe's greatest mysteries, dark matter. What if black holes aren't just destroyers of light, but also key players in the invisible web that holds the cosmos together? This is the intriguing question we'll explore next, as we dive into the connection between black holes and the elusive substance that makes up most of the universe's mass. What if the key to understanding one of the universe's greatest mysteries lies within the heart of a black hole, dark matter, the invisible substance that makes up about 85% of the universe's mass, has puzzled scientists for decades. We can't see it, touch it, or detect it directly, yet its gravitational effects are undeniable. Galaxies spin faster than they should, and cosmic structures bend light in ways that defy explanation. But could black holes, those cosmic enigmas we've been exploring, hold the key to unraveling the mystery of dark matter? The answer might surprise you. One intriguing theory suggests that black holes themselves could be made of dark matter. While most black holes we know of form from the collapse of massive stars, primordial black holes, smaller, hypothetical objects thought to have formed in the early universe, could be composed entirely of this elusive substance. Picture a universe filled with countless tiny black holes, no larger than an atom but packing the mass of a mountain. These black holes, if they exist, would be invisible, yet their gravitational pull would be felt across the cosmos. They could explain why galaxies rotate the way they do, and why the universe's structure seems to be held together by an invisible hand. It's a compelling idea, though one that remains unproven for now. But the connection between black holes and dark matter doesn't stop there. Some scientists propose that dark matter particles could interact with black holes in ways we've yet to detect. Imagine dark matter particles orbiting a black hole, gradually spiraling inward as they lose energy. Over time, these particles could accumulate near the event horizon, creating a halo of dark matter around the black hole. This halo could influence the black hole's behavior, altering how it grows, spins, or even emits radiation. If true, this interaction could provide a new way to study dark matter indirectly, using black holes as cosmic laboratories. To visualize this, think of the universe as a vast, interconnected web. Dark matter forms the scaffolding of this web, while galaxies and galaxy clusters are the nodes where the threads meet. Black holes, with their immense gravitational pull, act as anchors, drawing in both ordinary matter and dark matter. Together, they shape the large-scale structure of the cosmos, from the filaments of the cosmic web to the voids between galaxies. It's a delicate balance, one that underscores just how interconnected the universe truly is. The implications of this connection are profound. If black holes and dark matter are intertwined, it could revolutionize our understanding of the universe's evolution. Dark matter's gravitational influence is thought to have shaped the first galaxies, while black holes, with their ability to grow and merge, have played a crucial role in galaxy formation ever since. Together, they might hold the key to understanding how the universe grew from a sea of hot, dense gas into the complex, beautiful tapestry we see today. But the story doesn't end there. As we continue to explore the mysteries of black holes and dark matter, another question arises. Could these cosmic giants also play a role in the origin of cosmic rays? These high-energy particles, traveling at nearly the speed of light, bombard Earth from all directions, yet their sources remain largely unknown. What if black holes, with their immense gravitational fields and powerful jets, are the cosmic accelerators behind these mysterious particles? This is the frontier we'll explore next, as we dive into the fascinating connection between black holes and the high-energy phenomena that light up the cosmos. High-energy cosmic rays particles racing through space at nearly the speed of light have long been one of the universe's most intriguing mysteries. Where do these powerful particles come from, and what cosmic forces could possibly propel them to such incredible speeds? Surprisingly, the answer might lie in the most extreme environments in the universe, black holes. These cosmic giants, with their immense gravitational pull and energetic jets, could be the ultimate particle accelerators, capable of hurling particles across the cosmos with unimaginable force. But how does this process work, and what does it tell us about the universe's most energetic phenomena? To understand the connection between black holes and cosmic rays, let's start with the basics. Cosmic rays are not rays at all, they're actually high-speed atomic particles, mostly protons, that travel through space at nearly the speed of light. When these particles collide with Earth's atmosphere, they create showers of secondary particles that scientists can detect. But the journey of a cosmic ray begins far beyond our planet, in the most violent and energetic regions of the universe. And black holes, with their extreme environments, are prime candidates for producing these high-energy particles. One of the key mechanisms involves the powerful jets emitted by some black holes. When a black hole feeds on surrounding matter, it doesn't just swallow everything silently. Instead, some of the material is funneled into narrow, high-speed jets that shoot out from the black hole's poles at nearly the speed of light. These jets are like cosmic particle accelerators, powered by the black hole's immense gravity and magnetic fields. As particles spiral along the jet's magnetic field lines, they gain energy, reaching speeds so high that they become cosmic rays. It's a bit like a slingshot effect, where the black hole's gravity and magnetic forces work together to fling particles across the universe. But black holes aren't the only cosmic accelerators in the game. Supermassive black holes at the centers of galaxies, in particular, are thought to play a major role in producing the highest energy cosmic rays. When these colossal black holes consume matter, they release enormous amounts of energy, creating conditions that can accelerate particles to energies millions of times greater than those produced in the most powerful particle colliders on Earth. These ultra-high-energy cosmic rays are rare, but they carry clues about the most extreme processes in the universe, from the formation of galaxies to the behavior of matter under extreme conditions. To visualize this, imagine a black hole as a cosmic power plant. The accretion disk, a swirling ring of superheated gas and dust, acts like a generator, producing energy as matter spirals inward. Some of this energy is channeled into the jets, which act like high-speed conveyor belts, carrying particles away from the black hole at incredible speeds. As these particles travel through space, they interact with magnetic fields and other particles, eventually reaching Earth as cosmic rays. It's a journey that spans billions of light years, carrying with it the fingerprints of the black holes and other cosmic phenomena that shape their path. The implications of this connection are profound. By studying cosmic rays, scientists can learn about the processes that occur near black holes and other extreme astrophysical environments. These particles act as messengers, carrying information about the universe's most energetic events. They also provide a unique window into the behavior of matter and energy under conditions that we can't replicate on Earth. In this way, black holes aren't just cosmic enigmas, they're also powerful tools for exploring the universe's most fundamental questions. As we delve deeper into the mysteries of cosmic rays, another question emerges. What role do black holes play in the production of gamma-ray bursts, the most energetic explosions in the universe? These fleeting yet spectacular events, which outshine entire galaxies for a few seconds, are thought to be linked to black holes and other extreme astrophysical phenomena. The answers lie just ahead as we explore the explosive connection between black holes and gamma-ray bursts. Gamma-ray bursts, these are the universe's most powerful explosions, capable of releasing more energy in a few seconds than the sun will emit in its entire lifetime. But what causes these fleeting yet spectacular events? The answer, in many cases, lies in the same cosmic giants we've been exploring, black holes. Whether born from the collapse of a massive star or the merger of two black holes, gamma-ray bursts are among the most extreme phenomena in the cosmos, offering us a glimpse into the universe's most violent and energetic processes. Let's start with the collapse of a massive star, an event known as a hypernova. When a star many times more massive than our Sun exhausts its nuclear fuel, it doesn't just fade away, it goes out with a bang. The star's core collapses under its own gravity, forming a black hole, while the outer layers are blasted into space in an explosive shockwave. This explosion is so powerful that it sends out intense beams of gamma rays, the most energetic form of light. These beams, focused like cosmic laser pointers, can travel billions of light years, lighting up the universe in a brilliant flash. These are called long gamma-ray bursts, and they're thought to last anywhere from a few seconds to several minutes. They're the universe's way of signaling the birth of a black hole, a dramatic finale to the life of a star. But gamma-ray bursts aren't always the result of stellar collapse. Sometimes they're produced by the merger of two black holes or a black hole and a neutron star. When these incredibly dense objects spiral toward each other, their immense gravity generates ripples in spacetime gravitational waves and a burst of gamma rays. These short gamma-ray bursts last only milliseconds, but they pack an incredible punch, releasing more energy than a supernova. The collision creates a swirling maelstrom of matter and energy, with some of the material being ejected in the form of relativistic jets. These jets, traveling at nearly the speed of light, produce the gamma rays we detect. It's a cosmic fireworks show, one that reveals the universe's capacity for both creation and destruction. What makes gamma-ray bursts so important is not just their sheer power, but what they can tell us about the universe. Because they are so bright, they can be seen from the farthest reaches of space, acting as cosmic beacons that illuminate the early universe. When we detect a gamma-ray burst, we're essentially looking back in time, observing events that occurred billions of years ago. This makes them invaluable tools for studying the conditions of the early universe, from the formation of the first stars and galaxies to the distribution of matter across the cosmos. To visualize this, imagine a gamma-ray burst as a lighthouse in the dark expanse of space. Its beam cuts through the cosmic fog, revealing structures and processes that would otherwise remain hidden. Astronomers use these bursts to map the universe, measure distances, and even study the properties of spacetime itself. In this way, gamma-ray bursts are more than just explosions, they're windows into the universe's history and evolution. But detecting these bursts is no easy task. Gamma rays are absorbed by Earth's atmosphere, so we can't observe them from the ground. Instead, scientists rely on space-based telescopes like NASA's Fermi Gamma-Ray Space Telescope and the European Space Agency's Integral Mission. These instruments scan the skies for gamma-ray bursts, capturing their fleeting light and sending the data back to Earth. Once detected, astronomers use a network of ground-based telescopes to study the afterglow, the fading light that follows the initial burst. This afterglow provides crucial clues about the burst's origin, from the type of black hole involved to the environment in which it occurred. Gamma-ray bursts remind us that the universe is a dynamic and ever-changing place, where destruction often leads to creation. They also highlight the interconnectedness of cosmic phenomena, tying black holes to some of the most energetic events in existence. But the story doesn't end here. Just as black holes are linked to gamma-ray bursts, they also play a crucial role in another extreme astrophysical object, neutron stars. These incredibly dense remnants of stellar explosions are the universe's ultimate cosmic laboratories, and their connection to black holes opens up even more fascinating possibilities. In the cosmic ballet of stellar evolution, black holes and neutron stars are two of the most fascinating performers. Born from the ashes of supernova explosions, these dense remnants are the ultimate survivors of stellar cataclysms. Yet their stories don't end with their formation. Neutron stars, with their unimaginable density, and black holes, with their inescapable gravity, share a deep and dynamic relationship, one that can lead to some of the most extreme events in the universe. Let's explore this cosmic duo and how their interactions shape the fabric of spacetime itself. Neutron stars are the dense cores left behind after a massive star explodes in a supernova. Imagine squeezing the mass of the Sun into a sphere no larger than a city. This is the mind-bending reality of a neutron star. A single teaspoon of its material would weigh billions of tons on Earth. These stellar remnants are so dense that their gravity warps spacetime, creating intense magnetic fields and spinning at dizzying speeds, sometimes hundreds of times per second. But even these cosmic powerhouses have their limits. When a neutron star accumulates too much mass, either by merging with another neutron star or by pulling in matter from a companion star, it can cross a critical threshold. At this point, the star's gravity overwhelms the forces holding it together, and it collapses into a black hole. It's a cosmic transformation, turning one of the densest objects in the universe into an object where density becomes infinite. This collapse isn't just a theoretical curiosity, it's a process that has been observed indirectly through the detection of gravitational waves. When a neutron star and a black hole spiral toward each other, their immense gravity creates ripples in spacetime, much like waves spreading across a pond. As they merge, these ripples intensify, culminating in a burst of gravitational waves that can be detected billions of light-years away. The first confirmed neutron-star black hole merger was detected by LIGO and Virgo in 2019, marking a milestone in our understanding of these extreme cosmic events. Such mergers not only produce gravitational waves, but also unleash bursts of energy in the form of gamma rays and other electromagnetic radiation, offering a multi-messenger window into the universe's most violent processes. To visualize this, picture a neutron star orbiting a black hole. As they draw closer, the black hole's immense gravity begins to stretch and distort the neutron star, pulling material from its surface. This process, known as tidal disruption, creates a swirling disk of hot, glowing matter around the black hole, emitting intense radiation before the neutron star is finally consumed. The collision itself sends shockwaves through spacetime, detectable as gravitational waves, while the surrounding disk can produce a brilliant flash of light. It's a cosmic spectacle, one that reveals the intricate interplay between these two extraordinary objects, but the story doesn't end with the merger. The aftermath of such an event can have far-reaching consequences. The material ejected during the collision can seed the surrounding space with heavy elements like gold and platinum, enriching the cosmos with the building blocks of planets and life. Meanwhile, the newly formed black hole, now more massive than before, continues to shape its environment, influencing the motion of stars and gas in its vicinity. These interactions are part of the cosmic feedback loop, where the death of one star gives rise to new structures and possibilities. As we unravel the mysteries of neutron stars and black holes, we gain a deeper appreciation for the universe's complexity and interconnectedness. These objects are not just endpoints of stellar evolution, they are dynamic players in the cosmic drama, shaping the universe in ways we are only beginning to understand. And as we turn our gaze to the next chapter of this cosmic story, we'll explore how black holes, in their role as cosmic engines, power some of the brightest objects in the universe, quasars. These luminous beacons, shining from the edges of the observable universe, hold secrets about the early cosmos and the growth of supermassive black holes. But more on that in the next segment. At the heart of the universe's most luminous phenomena lies a fascinating partnership: black holes and quasars. Quasars, short for quasi-stellar radio sources, are the brightest objects in the cosmos, shining with the brilliance of trillions of stars. But what powers these celestial beacons? The answer lies in the supermassive black holes that lurk at their centers. These cosmic giants, millions or even billions of times more massive than our Sun, are the engines behind quasars, transforming vast amounts of matter into unimaginable energy. But how does this process work, and what role do quasars play in the story of the universe? Let's dive in. Quasars begin their lives in the hearts of galaxies, where supermassive black holes reside. As gas, dust, and stars are drawn toward the black hole, they form a swirling disk of superheated material known as an accretion disk. This disk isn't just a passive ring of debris, it's a seething cauldron of energy. Friction and magnetic forces within the disk heat the material to millions of degrees, causing it to glow across the electromagnetic spectrum, from radio waves to X-rays. But the real fireworks happen when some of this material is funneled into powerful jets that shoot out from the black hole's poles at nearly the speed of light. These jets, stretching for thousands of light years, are what make quasars so incredibly bright, outshining entire galaxies. It's as if the black hole is a cosmic powerhouse, converting matter into light on an unimaginable scale. To put this into perspective, imagine a single quasar emitting more energy in 1 second than our Sun will produce in its entire lifetime. This staggering output makes quasars visible from the farthest reaches of the universe, acting as cosmic lighthouses that pierce through the darkness of space. And because light takes time to travel, the quasars we observe today are actually snapshots of the universe's past. When we look at a quasar billions of light years away, we're seeing it as it was billions of years ago, offering a glimpse into the early universe. This makes quasars invaluable tools for astronomers, helping them map the cosmos and study its evolution. But quasars aren't just bright, they're also incredibly active. During the universe's infancy, when galaxies were still forming, quasars played a crucial role in shaping their surroundings. The intense radiation and powerful jets emitted by quasars heated the surrounding gas, preventing it from collapsing to form new stars. In this way, quasars acted as cosmic regulators, controlling the rate of star formation and influencing the growth of galaxies. They were like cosmic gardeners, pruning the universe's early structures and ensuring that galaxies evolved in a balanced and controlled manner. Without quasars, the universe as we know it might look very different. Visualizing a quasar is like imagining a cosmic tornado. At its center lies the supermassive black hole, pulling in matter with its immense gravity. Surrounding the black hole is the glowing accretion disk, a whirlpool of superheated gas and dust, and shooting out from the poles are the jets, narrow beams of charged particles that stretch across the cosmos, lighting up the surrounding space with their brilliance. It's a dynamic and chaotic scene, one that captures the raw power and beauty of the universe's most extreme environments. As we explore the connection between black holes and quasars, we gain a deeper appreciation for the universe's complexity and interconnectedness. These luminous objects are more than just cosmic oddities. They are windows into the universe's past, revealing the processes that shaped the cosmos in its earliest days. But the story doesn't end here. Quasars are just one piece of a larger puzzle, connected to a broader category of objects known as active galactic nuclei. These enigmatic structures, powered by supermassive black holes, play a central role in the evolution of galaxies, and their study offers even more insights into the universe's grand design. But more on that in the next segment. At the heart of some of the most luminous and dynamic galaxies in the universe lies a phenomenon that defies imagination: active galactic nuclei, or AN. These energetic cores, powered by supermassive black holes, are cosmic powerhouses, emitting vast amounts of energy across the electromagnetic spectrum. But what exactly are AGN, and how do black holes fuel their incredible activity? To understand this, we need to take a closer look at the relationship between these supermassive black holes and the galaxies they inhabit. Imagine a supermassive black hole, millions or even billions of times more massive than our Sun, lurking at the center of a galaxy. As stars, gas, and dust are pulled toward it by its immense gravity, they don't simply vanish into the void. Instead, they form a swirling disk of superheated material called an accretion disk. This disk isn't just a passive ring of debris, it's a seething, chaotic environment where friction and magnetic forces generate temperatures reaching millions of degrees. The result, a dazzling display of energy from radio waves to X-rays that can outshine the entire galaxy around it. This is the essence of an active galactic nucleus, a black hole surrounded by a glowing, energetic disk transforming matter into light on an almost incomprehensible scale. But AGN aren't just bright, they're also incredibly influential. The energy they release doesn't stay confined to the galactic center. It travels outward, shaping the galaxy in profound ways. For instance, the intense radiation from an AGN can heat the surrounding gas, preventing it from collapsing to form new stars. This process, known as feedback, acts as a cosmic thermostat, regulating star formation and ensuring that galaxies don't grow too quickly or chaotically. In some cases, the powerful jets emitted by AGN can even push gas out of the galaxy entirely, halting star formation altogether. It's a delicate balance, one that highlights the complex interplay between black holes and their host galaxies. To visualize this, picture an AGN as the heart of a galaxy, pumping energy and matter through its cosmic veins. The accretion disk glows brightly at the center, while jets of charged particles shoot out from the poles, stretching across thousands of light years. These jets can carve out vast cavities in the surrounding gas, creating intricate structures that resemble cosmic bubbles or filaments. And as the AGN's energy radiates outward, it interacts with the galaxy's stars, gas, and dust, influencing their motion and evolution. It's a dynamic and ever-changing system, one that reveals the profound impact black holes can have on their surroundings. The study of AGN isn't just about understanding individual galaxies, it's also about piecing together the broader story of cosmic evolution. By examining AGN in different galaxies, scientists can trace how black holes and galaxies have co-evolved over billions of years. For example, observations suggest that supermassive black holes and their host galaxies grow in tandem, with the black hole's mass closely linked to the properties of the galaxy itself. This connection hints at a deeper relationship, one where black holes aren't just passive residents of galaxies, but active participants in their growth and development. As we unravel the mysteries of AGN, we gain a deeper appreciation for the role black holes play in shaping the universe. These cosmic engines, with their immense energy and influence, are more than just destructive forces. They are creators, sculptors, and regulators, driving the evolution of galaxies and the cosmos as a whole. And as we continue to explore their secrets, we're led to yet another fascinating chapter in the story of black holes, their role in the formation and evolution of galaxy clusters. These vast cosmic structures, spanning millions of light years, are the largest gravitationally bound objects in the universe, and at their centers, supermassive black holes continue to shape the fabric of spacetime itself. But more on that in the next segment. Galaxy clusters are the universe's largest cities, vast metropolises of galaxies held together by gravity, spanning millions of light years. But what holds these cosmic cities together, and what keeps them from collapsing under their own immense weight? Surprisingly, the answer lies in the most unlikely of places, the supermassive black holes at the hearts of their galaxies. These black holes, often thought of as isolated destroyers, play a central role in shaping the dynamics of galaxy clusters, influencing everything from the flow of gas to the birth of stars. At the core of every galaxy cluster lies a supermassive black hole, millions or even billions of times more massive than our Sun. These cosmic giants are more than just gravitational anchors. They are active participants in the life of the cluster. As matter falls into the black hole, it forms an accretion disk, a swirling ring of superheated gas that glows brightly across the electromagnetic spectrum. But not all of this material is consumed. Some of it is expelled in powerful jets, narrow beams of charged particles that shoot out from the black hole's poles at nearly the speed of light. These jets can travel vast distances, heating the surrounding gas and preventing it from cooling and collapsing to form new stars. It's a cosmic balancing act, where the black hole's energy regulates the cluster's growth and evolution. One of the most fascinating aspects of this process is the heating of the intracluster medium, the diffuse gas that fills the spaces between galaxies in a cluster. Without the influence of black holes, this gas would cool and condense, leading to a burst of star formation, but the black hole's jets inject energy into the gas, keeping it hot and preventing it from collapsing. This feedback mechanism ensures that galaxy clusters evolve in a controlled manner, avoiding the chaotic bursts of star formation that could destabilize the cluster's structure. In this way, black holes act as cosmic thermostats, maintaining the delicate balance that allows galaxy clusters to thrive. To visualize this, imagine a galaxy cluster as a bustling city, with galaxies as buildings and the intracluster medium as the air between them. The supermassive black hole at the center is like a power plant, generating energy that flows through the city, heating the air and keeping the buildings from collapsing. The jets are like highways, carrying energy from the power plant to the farthest reaches of the city, ensuring that every corner remains warm and stable. It's a dynamic and interconnected system, one that highlights the profound influence black holes have on their surroundings. But the role of black holes in galaxy clusters goes beyond heating the intracluster medium. They also influence the motion of galaxies within the cluster, shaping its overall structure and dynamics. For example, the gravitational pull of a supermassive black hole can affect the orbits of nearby galaxies, causing them to move in predictable patterns. This interaction helps maintain the cluster's cohesion, preventing galaxies from drifting apart. At the same time, the black hole's energy can push gas out of the cluster, creating voids and filaments that give the cluster its distinctive appearance. These processes are part of the cosmic feedback loop, where black holes and galaxies work together to shape the largest structures in the universe. As we explore the intricate relationship between black holes and galaxy clusters, we gain a deeper appreciation for the universe's complexity and interconnectedness. These cosmic giants are not just destructive forces, they are creators and regulators, shaping the evolution of galaxies and clusters on a grand scale. And as we continue to probe their secrets, we're led to yet another fascinating chapter in the story of black holes, their role in the study of the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light holds clues about the universe's origins and evolution, and black holes play a surprising part in unlocking its secrets, but more on that in the next segment. When we look up at the night sky, we're not just seeing stars and galaxies, we're peering into the past. The light from distant objects has traveled billions of years to reach us, carrying with it echoes of the universe's earliest moments. But the most ancient light of all isn't visible to the naked eye. It's the cosmic microwave background, or CMB, the faint afterglow of the Big Bang that fills the entire cosmos. This relic radiation, discovered in the 1960s, is like a snapshot of the universe when it was just 380,000 years old. And hidden within its subtle variations might be clues not just about the Big Bang, but about something even more mysterious: primordial black holes. Primordial black holes, as we've touched on earlier, are hypothetical objects thought to have formed in the chaotic aftermath of the Big Bang. Unlike the black holes we're familiar with today, which are born from the collapse of massive stars, primordial black holes could have emerged from the tiniest fluctuations in density in the early universe. These fluctuations, regions where matter was packed slightly tighter than the surrounding space, could have collapsed under their own gravity, forming black holes of all sizes, from the mass of a mountain to that of a star. But how do these ancient black holes connect to the CMB? The answer lies in the subtle imprints they may have left on this ancient light. Imagine the early universe as a hot, dense soup of particles and radiation. As the universe expanded and cooled, this soup began to thin out, allowing photons, particles of light, to travel freely for the first time. These photons, now stretched into microwaves by the expansion of the universe, form the CMB we observe today. But if primordial black holes existed in this early soup, their immense gravity could have influenced the distribution of matter and energy, leaving faint signatures in the CMB's temperature and polarization patterns. These imprints would be like cosmic fingerprints, offering clues about the presence of these ancient black holes and the conditions of the early universe. Scientists have been searching for these fingerprints for decades, analyzing the CMB with ever-increasing precision. Satellites like NASA's WMAP and the European Space Agency's Planck have mapped the CMB in exquisite detail, revealing tiny temperature fluctuations that correspond to regions of slightly higher or lower density in the early universe. Some of these fluctuations could be the result of primordial black holes, their gravity subtly warping the fabric of spacetime and leaving behind a telltale signature. While no definitive evidence has been found yet, the search continues, with new missions and technologies promising to bring us closer to an answer. The implications of finding such imprints would be profound. Primordial black holes could explain some of the universe's greatest mysteries, from the nature of dark matter to the origins of the cosmic structures we see today. They might also provide insights into the physics of the early universe, shedding light on the conditions that gave rise to everything we know. In this way, the CMB isn't just a relic of the past, it's a cosmic detective, helping us piece together the story of how the universe came to be. As we ponder the connection between black holes and the CMB, we're reminded of just how interconnected the cosmos truly is. Every observation, every discovery, adds another piece to the puzzle, revealing the intricate web of forces and phenomena that shape our universe. But the story doesn't end here. As we continue to explore the mysteries of black holes, another question arises. What role do these cosmic giants play in the expansion of the universe itself? This is the frontier we'll explore next, as we dive into the fascinating relationship between black holes and the accelerating expansion of the cosmos. As we journey deeper into the mysteries of black holes, we encounter one of the most profound questions in modern cosmology. What role do these cosmic giants play in the accelerating expansion of the universe? For decades, scientists have known that the universe isn't just expanding, it's doing so at an ever-increasing rate, driven by a mysterious force called dark energy. But could black holes, those enigmatic destroyers of light, also be contributing to this cosmic acceleration? The answer might lie in the interplay between gravity and the very fabric of spacetime itself. At first glance, black holes and dark energy seem like polar opposites. Black holes are concentrations of gravity so intense that nothing can escape their pull, while dark energy is the force pushing the universe apart, stretching spacetime on the largest scales. Yet, recent theories suggest that black holes might not just be passive players in this cosmic drama, they could actually be sources or sinks of dark energy. Imagine a black hole as a cosmic sponge, absorbing or releasing this mysterious force as it evolves. This idea stems from the observation that black holes grow not only by swallowing matter, but also by interacting with the energy that permeates the universe. If true, this would mean that black holes are deeply intertwined with the fate of the cosmos, shaping its expansion in ways we're only beginning to understand. One compelling theory proposes that black holes could act as reservoirs of dark energy, storing it within their event horizons. As the universe expands, the energy density of dark energy remains constant, meaning more of it is created as space stretches. Some scientists suggest that black holes might absorb this excess energy, effectively acting as cosmic batteries that regulate the universe's expansion. In this scenario, black holes aren't just endpoints for matter, they are dynamic participants in the cosmic balance, influencing the very structure of spacetime. But what does this mean for the ultimate fate of the universe? If black holes are indeed connected to dark energy, their role could be crucial in determining how the cosmos evolves. One possibility is the Big Rip, a scenario where dark energy becomes so dominant that it tears apart galaxies, stars, and even atoms themselves. In this dramatic endgame, black holes might be the last structures standing, their immense gravity resisting the relentless pull of dark energy, at least for a while. Another possibility is the heat death, where the universe expands so much that it becomes cold, dark, and empty, with black holes slowly evaporating over trillions of years through Hawking radiation. Both scenarios paint a stark picture of the cosmos, and black holes could play a pivotal role in determining which path the universe ultimately takes. To visualize this interplay, imagine the universe as a vast, expanding fabric. Dark energy stretches this fabric outward, while black holes act like weights, creating deep dimples that tug at the surrounding material. Over time, these dimples could influence how the fabric stretches, altering the rate and direction of cosmic expansion. It's a delicate dance between two opposing forces, one that could shape the destiny of everything we know. As we explore this cosmic tug-of-war, we're reminded of just how interconnected the universe truly is. Black holes, once thought of as isolated oddities, are now being seen as key players in the grand cosmic drama. Their relationship with dark energy not only deepens our understanding of these mysterious forces, but also raises profound questions about the nature of existence itself. And as we continue to unravel these mysteries, we're led to yet another tantalizing possibility. Could black holes hold the key to understanding the multiverse? This is the frontier we'll explore next, as we venture into the realm of parallel realities and the cosmic bridges that might connect them. What if the black holes we've been exploring aren't just cosmic anomalies in our universe, but gateways to entirely new ones? This is the tantalizing idea at the heart of the multiverse theory, a concept that suggests our universe might be just one of countless others, each with its own unique laws of physics and possibilities. And at the center of this theory lies one of the most intriguing questions of all. Could black holes, those enigmatic destroyers of light, also be bridges to other realities? Recent advancements in physics are bringing us closer to answering this question, offering glimpses into a cosmos far stranger and more interconnected than we ever imagined. One of the key ideas supporting the multiverse theory is the holographic principle, which suggests that all the information about a three-dimensional space can be encoded on its two-dimensional boundary. Think of it like a hologram, where a flat surface contains all the data needed to project a 3D image. In the context of black holes, this principle implies that the information about everything that falls into a black hole isn't lost. It's preserved on the event horizon, the black hole's surface. Some scientists take this a step further, proposing that this encoded information could act as a kind of cosmic portal, connecting our universe to another. It's as if the event horizon is a screen showing a movie of another universe, with the black hole itself serving as the projector. But the holographic principle isn't the only clue pointing to a multiverse. Quantum entanglement, the phenomenon where particles become linked across vast distances, also hints at deeper connections between realities. In this strange quantum world, particles can influence each other instantaneously, no matter how far apart they are. Some theories suggest that this entanglement could extend beyond our universe, linking particles in parallel realities. If true, black holes might play a role in this cosmic network, acting as nodes that connect different universes through quantum pathways. It's a mind-bending idea, but one that's grounded in real physics. The philosophical implications of a multiverse are just as profound as the scientific ones. If black holes truly are gateways to other universes, what does that mean for our understanding of reality? Are there infinite versions of us, living out every possible outcome of our decisions? Or do these parallel realities operate under entirely different laws, creating worlds that are unimaginably alien? These questions push us to rethink not just our place in the cosmos, but the very nature of existence itself. They remind us that the universe is far more complex and mysterious than we can currently comprehend. To bring this idea to life, let's imagine a hypothetical scenario. Picture an astronaut venturing close to a black hole's event horizon. As they approach, time slows down dramatically, stretching seconds into years. But what if, at the moment they cross the horizon, they don't vanish into oblivion? Instead, they emerge in another universe, one where the laws of physics are entirely different. Perhaps in this new reality, gravity works in reverse, or time flows backward. It's a speculative scenario, but one that captures the imagination and highlights the possibilities that black holes and the multiverse theory present. As we ponder these extraordinary ideas, we're reminded that the study of black holes isn't just about unraveling cosmic mysteries, it's also about expanding our understanding of what's possible. And as we continue to explore these enigmatic objects, we're led to yet another fascinating question. Could black holes also hold clues in the search for extraterrestrial intelligence? This is the frontier we'll explore next, as we dive into the possibility that these cosmic giants might be more than just gateways. They could be beacons, signaling the presence of civilizations far beyond our own. When we think about the search for extraterrestrial intelligence, black holes might not be the first place we'd look. After all, these cosmic behemoths are known for their destructive power, ripping apart stars and consuming anything that ventures too close. But what if the story isn't so straightforward? What if, hidden in the chaos of these extreme environments, advanced civilizations have found ways to harness black holes for their own purposes, perhaps even using them as tools for communication, travel, or energy? This idea might sound like science fiction, but it's rooted in real scientific theories and offers a fascinating perspective on the search for life beyond Earth. One of the most intriguing possibilities is that black holes could serve as cosmic lighthouses for advanced civilizations. Imagine a society so technologically advanced that they've learned to manipulate the immense energy of a black hole's accretion disk. The glowing ring of superheated gas and dust, visible across vast distances, could act as a beacon, signaling their presence to other intelligent beings. Some scientists have even speculated that megastructures, like Dyson spheres, hypothetical constructs designed to capture the energy of a star, could be built around black holes. Instead of surrounding a star, a Dyson sphere could envelop a black hole's accretion disk, harnessing its incredible energy output. Such a structure would be visible from across the universe, serving as a clear marker of intelligent life. But black holes could be more than just energy sources or beacons. They might also function as cosmic highways. The extreme warping of spacetime near a black hole could, in theory, create shortcuts through the universe, known as wormholes. These hypothetical tunnels could allow for faster-than-light travel, connecting distant regions of space or even different universes. If an advanced civilization discovered how to stabilize and navigate these wormholes, black holes could become the ultimate interstellar travel hubs. Picture a network of black hole gateways, enabling civilizations to traverse the cosmos in ways we can barely imagine. While this remains speculative, it's a tantalizing idea that highlights the potential for black holes to play a role in the cosmic exchange of ideas, cultures, and technologies. The search for extraterrestrial intelligence, or SETI, has traditionally focused on detecting radio signals or other signs of technological activity. But if civilizations are using black holes as part of their infrastructure, our approach might need to expand. Instead of listening for faint signals, we could look for unusual patterns around black holes, signs of artificial structures, energy harvesting, or even the manipulation of spacetime itself. These phenomena, though difficult to detect, could provide the first clues that we're not alone in the universe. It's a shift in perspective that challenges us to think beyond traditional methods and consider the vast possibilities that black holes present. Of course, these ideas are speculative, but they're grounded in real physics and offer a fresh lens through which to view the search for intelligent life. They remind us that the universe is full of mysteries waiting to be uncovered, and that advanced civilizations might operate in ways we've yet to imagine. As we continue to explore these possibilities, we're led to yet another profound question. What role do black holes play in our understanding of time? This is the frontier we'll explore next, as we delve into the mind-bending ways black holes challenge our perception of past, present, and future. Time is one of the most fundamental aspects of our existence, yet near a black hole, it becomes a malleable, almost surreal concept. The immense gravitational pull of a black hole doesn't just warp space, it bends time itself, creating effects that challenge our everyday understanding of reality. This phenomenon, known as time dilation, is one of the most striking predictions of Einstein's theory of general relativity. To grasp its implications, let's imagine two astronauts. One stays far from a black hole, while the other ventures close to its event horizon. To the distant astronaut, time for their companion appears to slow down dramatically. Minutes near the black hole could stretch into years or even centuries for the observer far away. It's as though the black hole's gravity acts like a cosmic time machine, stretching moments into eons. To make this even more relatable, consider the classic twin paradox. Imagine twins born on Earth. One decides to embark on a journey near a black hole, while the other remains at home. When the traveling twin returns, they might find their sibling has aged decades, while they themselves have only experienced a few years. This isn't science fiction, it's a direct consequence of how gravity warps time. Near a black hole, the fabric of spacetime is so distorted that time itself slows to a crawl, creating a rift between the experiences of those inside and outside its gravitational influence. But time dilation isn't just a curious quirk of physics, it has profound implications for our understanding of causality and the nature of reality. If time can stretch and warp, what does that mean for the concept of cause and effect? Could events near a black hole occur in a different order depending on where you're observing them from? These questions push us to rethink the very foundations of how we perceive the universe. They also open the door to speculative ideas about time travel, where black holes might serve as gateways to the past or future. While these concepts remain theoretical, they highlight just how deeply black holes challenge our understanding of time and existence. As we explore these mind-bending ideas, it's worth considering what they mean for our place in the cosmos. If time is not the rigid, unchanging force we once thought, but rather a fluid, dynamic dimension influenced by gravity, then the universe is far more interconnected and complex than we ever imagined. Black holes, with their ability to warp time, are not just cosmic oddities, they are windows into the deepest mysteries of reality, offering clues about the nature of existence itself. But the story doesn't end with time. Black holes also play a pivotal role in shaping the very fabric of space, influencing the motion of stars, galaxies, and even the structure of the universe itself. As we turn our gaze to this next frontier, we'll uncover how these cosmic giants sculpt the cosmos, revealing a universe that's as dynamic as it is mysterious. Black holes don't just devour light and matter, they twist and stretch the very fabric of space itself. Imagine space as a vast, invisible sheet stretched taut, with stars and galaxies resting gently on its surface. Now, place a black hole on that sheet. The immense gravity of the black hole creates a deep, funnel-shaped dent, warping the space around it like a cosmic whirlpool. This isn't just a metaphor, it's a real phenomenon predicted by Einstein's theory of general relativity. And it's this warping of space that gives rise to some of the most fascinating effects in the universe, from gravitational lensing to the mind-bending concept of singularities. One of the most striking examples of this warping is gravitational lensing. When light from a distant star or galaxy passes near a black hole, the intense gravity bends the light's path, much like a magnifying glass bends light. This effect can create stunning visual phenomena, such as multiple images of the same object appearing around the black hole, or even a glowing ring of light known as an Einstein ring. These cosmic mirages aren't just beautiful, they're also incredibly useful. Astronomers use gravitational lensing to study objects that would otherwise be too distant or faint to observe, effectively turning black holes into natural telescopes. It's as if the universe has given us a tool to peer deeper into its mysteries, using the very objects that once seemed impenetrable. But the warping of space near a black hole goes far beyond bending light. At the heart of every black hole lies a singularity, a point where the fabric of space and time breaks down completely. Here, the laws of physics as we know them cease to function, and concepts like distance and direction lose all meaning. It's a place where matter is compressed to infinite density, and the very rules that govern the universe are rewritten. While we can't observe a singularity directly, it's hidden behind the event horizon. Its existence challenges our understanding of reality, pushing us to rethink the nature of space and time. Some theories even suggest that singularities could be gateways to other dimensions or hidden regions of the universe, hinting at a cosmos far more complex than we've ever imagined. To grasp the full implications of these ideas, let's zoom out and consider the broader picture. Black holes aren't just isolated oddities, they're cosmic laboratories, testing the limits of our physical theories. General relativity, which describes gravity and the large-scale structure of the universe, works beautifully when applied to black holes. But when we try to combine it with quantum mechanics, the science of the very small, things start to fall apart. The singularity at the heart of a black hole, represents a breakdown in our understanding, a place where the two theories collide and fail to reconcile. This tension has led scientists to explore new ideas, from string theory to loop quantum gravity, in search of a unified framework that can explain the universe on all scales. Visualizing this warping of space can be challenging, but imagine standing near a black hole. As you approach, the stars around you would appear distorted, their light stretched and twisted by the black hole's gravity. If you were to look directly at the black hole, you might see a dark void surrounded by a glowing ring of light, the distorted image of the accretion disk. And if you could peer beyond the event horizon, you'd find yourself in a place where the rules of space and time no longer apply. It's a realm of infinite density and infinite mystery, a place where the universe itself seems to unravel. As we explore these mind-bending concepts, one thing becomes clear: black holes are more than just cosmic curiosities. They are keys to unlocking the deepest secrets of the universe. They challenge us to think beyond the limits of our current understanding, offering glimpses of a reality far stranger and more interconnected than we ever imagined. And as we continue to probe their mysteries, we're led to yet another profound question: how did black holes shape the early universe? This is the frontier we'll explore next, as we journey back in time to uncover the origins of these cosmic giants and their role in the birth of the cosmos. To understand the origins of the universe, we need to journey back to the very beginning, a time when the cosmos was a swirling sea of energy, hotter and denser than anything we can imagine. This is the realm of the Big Bang, the moment when space and time as we know them began. But what if black holes, those enigmatic destroyers of light, were also there at the dawn of the universe? What role could they have played in shaping the cosmos we see today? The answer lies in one of the most intriguing ideas in modern cosmology: primordial black holes. Unlike the black holes we're familiar with, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the chaotic moments following the Big Bang. Picture the early universe as a bubbling cauldron of energy, with tiny fluctuations in density scattered throughout. In some regions, matter was packed slightly tighter than in others. Under the immense pressure of the universe's rapid expansion, these dense pockets could have collapsed into black holes. These primordial black holes, ranging in size from subatomic scales to the mass of entire stars, would have been among the first structures to form in the cosmos. They're like cosmic fossils, relics from a time when the universe was in its infancy. But why does this matter? Primordial black holes could hold the key to some of the universe's greatest mysteries. For instance, they might explain the nature of dark matter, the invisible substance that makes up most of the universe's mass. While we can't see dark matter directly, its gravitational effects are undeniable. Galaxies rotate faster than they should, and cosmic structures bend light in ways that defy explanation. Some scientists propose that primordial black holes could make up at least a portion of this elusive substance. Imagine a universe filled with countless tiny black holes, invisible yet omnipresent, weaving the cosmic web of dark matter that holds galaxies together. It's a compelling idea, though one that remains unproven for now. To visualize this early universe, think of it as a vast, expanding sea of energy and matter, punctuated by these gravitational hotspots. As the universe cooled and expanded, primordial black holes would have grown, merging with one another and influencing the distribution of matter around them. Over billions of years, their combined effects could have shaped the large-scale structure of the cosmos, from the filaments of the cosmic web to the clusters of galaxies we observe today. It's a cosmic dance where black holes lead the way, guiding the universe's evolution from chaos to order. The implications of this idea are profound. If primordial black holes played a role in the universe's formation, they could help us understand how galaxies and galaxy clusters came to be. They might also shed light on the processes that gave rise to the first stars and the elements that make up everything we see, including us. In this way, black holes aren't just destroyers of light, they're also creators, sculpting the universe in ways we're only beginning to comprehend. But the story doesn't end in the distant past. As we continue to explore these cosmic beginnings, another question arises. How do black holes shape the universe's ultimate fate? From the Big Bang to the far future, black holes are cosmic architects, influencing the universe's evolution in ways that are as profound as they are mysterious. But more on that in the next segment. As we peer into the distant future of the universe, black holes emerge as central players in the cosmic drama of its ultimate fate. Theories about how the universe might end, whether in a fiery Big Crunch, a cold heat death, or a dramatic Big Rip, all hinge on the interplay between gravity, dark energy, and the enigmatic behavior of these gravitational giants. But how exactly do black holes fit into these scenarios, and what might their role tell us about the universe's final chapter? Let's dive into the possibilities, each one more fascinating and unsettling than the last. One of the most dramatic endgame scenarios is the Big Crunch, a theory suggesting that the universe could eventually stop expanding and collapse back in on itself. In this scenario, gravity, the force that binds galaxies and stars together, would ultimately overcome the outward push of dark energy. As galaxies merge and black holes grow, their gravitational pull would draw everything closer, accelerating the collapse. Over time, supermassive black holes at the centers of galaxies would devour stars, gas, and even other black holes, growing larger and more dominant. Eventually, the universe would shrink to a single point of infinite density, a cosmic mirror of the Big Bang. It's a poetic symmetry, but one that raises profound questions. Would time itself reverse in such a collapse? And what, if anything, would remain afterward? On the opposite end of the spectrum lies the heat death, a far colder and quieter fate. In this scenario, the universe continues to expand indefinitely, driven by dark energy. As space stretches, matter and energy become increasingly diluted, and stars burn out one by one. Black holes, once the most formidable structures in the cosmos, would slowly evaporate through a process known as Hawking radiation. Over trillions of years, these cosmic giants would release their energy back into the universe, fading into nothingness. Eventually, the universe would become a vast, cold void, with no sources of heat or light remaining. It's a sobering thought, but one that highlights the transient nature of even the most powerful forces in the cosmos. Then there's the Big Rip, a scenario where dark energy grows so dominant that it tears the universe apart. In this dramatic end, the expansion of space accelerates to such an extreme rate that galaxies, stars, and even atoms are ripped apart. Black holes, with their immense gravity, might resist this fate longer than anything else, but even they would eventually succumb. As spacetime stretches to its breaking point, black holes would be torn asunder, their singularities exposed, and their event horizons dissolved. It's a violent and chaotic end, one that underscores the fragility of the cosmic order we take for granted. These scenarios aren't just speculative, they're windows into the fundamental forces that shape our universe. Black holes, with their ability to warp space-time and consume matter, play a pivotal role in each one. They remind us that the universe is a dynamic ever-changing place, where even the most stable structures are subject to the relentless march of time. And as we ponder these possibilities, we're led to reflect on the nature of existence itself. What does it mean for time and space to end, and what, if anything, comes after? As we stand on the edge of these cosmic mysteries, it's impossible not to feel a sense of awe and humility. Black holes, once thought of as isolated destroyers, are now seen as integral to the universe's grand narrative. They challenge us to think beyond the limits of our understanding, offering glimpses of a reality far stranger and more interconnected than we ever imagined. And as we continue to explore their secrets, we're reminded that the journey of discovery is just as important as the answers we seek. But the story doesn't end here. As we reflect on the role of black holes in the universe's ultimate fate, another question arises: what have we learned from our journey into the heart of these cosmic enigmas? From their formation to their influence on galaxies and beyond, black holes have reshaped our understanding of the cosmos and ourselves. This is the question we'll explore next, as we take a step back to consider the profound impact of black holes on science, philosophy, and the human spirit. As we near the end of this cosmic journey, it's worth taking a moment to reflect on the extraordinary path we've traveled together. From the first theoretical musings of John Michell and Pierre-Simon Laplace, who dared to imagine stars so massive that even light couldn't escape, to the groundbreaking discoveries of today, like the first image of a black hole's event horizon and the detection of gravitational waves, our understanding of these enigmatic objects has grown in leaps and bounds. Black holes, once dismissed as mere mathematical curiosities, have become central to our exploration of the universe, reshaping not just the field of astrophysics, but also our philosophical understanding of reality itself. At every turn, black holes have challenged us to rethink what we thought we knew. They've shown us that space and time are not rigid and unchanging, but dynamic and malleable, bending under the immense gravity of these cosmic giants. They've forced us to confront profound questions about the nature of existence, from the fate of information swallowed by their event horizons to the possibility of parallel universes lurking beyond their singularities. And they've revealed their surprising role in the larger cosmic story, acting as both destroyers and creators, tearing apart stars and galaxies while seeding the universe with the raw materials needed for new structures to form. But perhaps the most remarkable aspect of this journey is how black holes have brought together diverse fields of science. The study of these cosmic enigmas has united astrophysics with quantum mechanics, general relativity with particle physics, and even philosophy with cosmology. They've pushed us to develop new technologies, from the Event Horizon Telescope to gravitational wave detectors like LIGO, and inspired bold new theories that stretch the boundaries of human imagination. In this way, black holes are more than just objects of study. They are catalysts for discovery, driving us to explore the unknown and expand the frontiers of knowledge. As we reflect on these insights, it's impossible not to feel a sense of awe and wonder. Black holes remind us that the universe is far stranger and more beautiful than we ever imagined, filled with mysteries waiting to be uncovered. They challenge us to think beyond the limits of our current understanding, to ask questions that push the boundaries of science and philosophy, and they invite us to consider our place in the cosmos, not as passive observers, but as active participants in a grand, interconnected story. So, as we prepare to conclude this exploration, let's take a moment to appreciate the journey we've shared. From the birth of black holes in the fiery aftermath of supernova to their role in shaping the largest structures in the universe, From their mysterious singularities to their potential as cosmic gateways, black holes have captivated our imaginations and deepened our understanding of the cosmos. But the story doesn't end here. Every discovery raises new questions, every insight opens new doors, and every mystery invites us to keep exploring. In the final segment of this video, we'll tie together the threads of this cosmic tapestry, reflecting on the overarching themes of black holes and their profound implications for science, philosophy, and our understanding of the universe. From their role in the early universe to their influence on its ultimate fate, black holes are more than just cosmic oddities. They are keys to unlocking the deepest secrets of existence. So, join me as we take one last step into the heart of these enigmatic giants and uncover what they can teach us about the universe and ourselves. As we bring this journey to a close, let's take a moment to reflect on the incredible story of black holes, cosmic giants that have reshaped our understanding of the universe. From their violent birth in the collapse of massive stars to their role as gravitational anchors at the heart of galaxies, black holes have proven to be far more than just cosmic vacuum cleaners. They are creators and destroyers, regulators and gateways, sculpting the cosmos in ways we're only beginning to comprehend. We've explored how they warp space-time, bend light, and even challenge the very laws of physics, pushing us to rethink concepts like time, information, and reality itself. Yet for all we've learned, black holes remain shrouded in mystery, the singularity at their core, a point of infinite density where the known laws of physics break down continues to defy explanation. Could it be a portal to another universe, a bridge to alternate realities, or something entirely beyond our imagination? The answers to these questions lie hidden behind the event horizon, a boundary that keeps their deepest secrets just out of reach. And while we've made incredible strides, from capturing the first image of a black hole to detecting gravitational waves from their collisions, there's still so much we don't know. What happens inside a black hole? Is information truly lost, or is it somehow preserved? And what does it all mean for the nature of existence? These enduring mysteries remind us that the universe is far stranger and more wondrous than we can imagine. They invite us to keep exploring, to keep questioning, and to embrace the unknown. As Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And in the case of black holes, that something could rewrite the story of the cosmos itself. So, as we wrap up, I leave you with this thought: what lies beyond the event horizon, and what does it reveal about the nature of existence? The answers may lie in the next discovery, the next breakthrough, or even the next question you ask. Share your thoughts in the comments below. What fascinates you most about black holes? And if you've enjoyed this journey into the heart of these cosmic enigmas, don't forget to subscribe for more explorations of the universe's greatest mysteries. Together, let's keep uncovering the secrets of the cosmos, one question at a time. The universe is vast, and the adventure is just beginning.